Welcome to a lesson with Dr. Powell. Let's talk about how we can find components of one vector on another one with complex numbers. First of all, let's take two vectors like this. Let's suppose this is v and w. Okay, these two vectors can be thought of as complex numbers since their tips have coordinates in the xy plane. So you can think of, v as being like a plus bi, where we just take this as ab as the coordinate of the tip. Similarly, w could be something else, c plus di, and the coordinates of the tip are just it's like cd, and they both stem from the origin. Okay, so you can think of vectors as being complex numbers. Now, what are we looking for? If we take v and we think of w as being kind of like a plane or something flat, an incline, and kind of like the ground. So one of the vectors will be the ground. Let's suppose w is the ground. And v is a vector that comes kind of out of the ground. Then what we'd like to do is think of something coming from the ground perpendicularly up to the tip here. So from the ground up perpendicular up to the tip of the other one, and you have this right triangle where the right angle is always on the ground because that's the right place to be. Okay, so then what we have is we have two different components of the vector v in relation to w. And there's different names for this and different terminology. So if you take the vector v and you think about the length that comes from here to here, it's kind of like the component of v in the direction of w. And we can write that like this, like the component of v on w. So notice how w is written below, v is above, because it's v on w, like v is on top of w, like because w is the ground. The ground always goes down here as a subscript, as it should be because it's lower. So the component of v on the ground w is equal to that length. Okay, so maybe we'll call this length here. Let's call this maybe L1, and this one L2 would be is another length here, and we'll talk about that length in a minute. Okay, so we have these two different lengths, and this length L1, we have a notation for it. L1 is equal to the component on w of v, so kind of like the projection of v onto w. Another notation for this is we could write the projection of v onto w, but this notation is different because this notation is a length, and lengths when we're dealing with vectors are often called scalars because you can multiply a vector by something to rescale it by a number, and so numbers are called scalars when we're talking about vectors. So this right here is a scalar because it's a number, and then this is actually a vector. Which vector is it? It's actually the vector that goes right up to that point here on the ground where we're going up of length L1. So this is actually, we can label this maybe as another vector, call it maybe, it's on the, maybe we'll call it the vector G. How's that? Vector G. Okay, that's along the ground. So the projection is actually a vector along the ground. It's kind of like the shadow vector. It has length. The length of it is, the length of this vector is actually L1. We could think about, so in terms of notation, we can use absolute value symbol because it means like distance from the origin, and quite literally it's the distance from the tip to the origin. Or you can think of magnitude or length that's going to be also equal to L1. Okay, so we kind of have that set up here. This is what we want to be looking for. Let's use complex numbers to actually find this L1 and this L2. Okay, how do we find L1 and L2 in complex numbers? All right, so we're going to think of, okay, so let's think of V as just being a complex number now. Let's think of W as being a complex number. And what we'd like to do is rotate our picture. So W is just on the ground here. It's supposed to be straight. And V is, so V and W. Let's get that a little straighter here. Okay, so that's W. And we have V. Okay, so we'd like to rotate this picture. So this angle right here is the same as that angle right there. Well, if you noticed when we had a description of what happens with complex multiplication with plotting with another coordinate system, what always happens, there's two things that happen. The whole picture rotates so that one direction is now the new x-axis. So you have a rotation, and you also have maybe an expansion or compression, depending on what is your new unit length. So those are the two things that happen. Now, in this process, angles stay the same. So angles are preserved from doing the multiplication to afterwards. So what we'd like to do is multiply this V and W by something that sends the picture right here via rotation. Now, what we multiply by could also have an expansion, and that's okay. But at least the angle will be preserved. So let's think about that for a minute. All right. So how do we get W to come down to be on the x-axis? Want W to kind of come down to the x-axis. So, all right. So what's going to be the new x-axis that we're going to be plotting against? Well, what if, so we want this angle right here. Okay, this angle is now to this x-axis. If we're plotting W with respect to another axis, it's going to be that much above that axis, which means we go down here. So the axis that we want, the new axis, should be down here. How do you get that? Well, you simply take, so if W is equal to C plus DI, you simply go to downward to C minus DI, where you just take the negative of the or you just change the sign of the imaginary part. That process is actually called complex conjugation. So W bar is called the conjugate of W. It's just simply same as W, but just down below it. So if we were to multiply this whole picture by W bar, what would happen is this would come down to the x-axis, and this angle would be preserved. So this would be kind of like, so the x-axis will be right where this is, and then this will be up here. VW bar. So let's look at VW bar and see what it's going to look like now. So VW bar is going to look like this. VW bar, and W is actually going to be right along the ground now, at least when we've multiplied it by W bar, okay? And we have the right angle that we need. Now, or the angle that we wanted. Okay, so imagine this is on the x-axis, but let's turn our picture so that we're actually, so this looks a little flatter. Okay, flatter. Okay, so it looks horizontal. All right, imagine this is horizontal here, and the angle has been preserved. It's just been rotated down. Now, what happens if, so this is going to have a real part and imaginary part. You know, this is going to be like some kind of, let's just suppose this is A plus BI for now. Then that means that this will be A and this will be B. Another way of writing that is just to say the real part of VW bar is this right here. and the imaginary part is this right here. So we got real and we got imaginary. Now, in this process, we've multiplied by W bar and it's rotated things, but it's also given us a new unit length, which has expanded everything. In fact, it's expanded everything by the length of what we're multiplying by. Now, the length of what we're multiplying by is actually the same as the length of W. I mean, the complex conjugate is just a rotation of W, just straight, just down. So we could just take the length of, so if you just take the length of W, and that's what everything's been expanded by. So if we unexpand it, just divide everything by that length, voila, we actually have the distances that we were interested in the beginning. This is L1, and this is L2. So we can compute these distances using the real part of this complex multiplication and the imaginary part of this complex multiplication. Notice that in this process, we didn't even use this quantity at all. We're just simply using, because we're focusing on how V is in relation to the ground. So we just needed to get this to the ground, that's all. And then we're just looking at the imaginary part and the real part. So in the next video, we'll actually work through an example of this idea and how to use it so that we can actually compute the imaginary part and the real part of this, which will give us this component and that component of the vector. So this is like the orthogonal component or perpendicular component, if you will. And this one right here is the it's just the regular component along the vector, or V along the ground, just kind of casting a shadow straight down that way. Okay, so watch the next video to see an example. Thanks for watching.